The purpose of this short video is to explain how to design a jog detector and show some example results. Now, without a doubt, there are other ways to go about this, and some are riskier than others in terms of success, but this approach will get the job done in a way that we can confirm the jog detector works. A jog detector is a sensor device used against the seeker of a radar homing missile. Its purpose is to indicate when the ECM has caused a seeker antenna pointing error. A jog detector is useless by itself. It is only useful if it triggers an action, so it is logically always a subsystem. It's part of something else, for example, a jammer. The angle error can come from active onboard angle deception countermeasures or an off-board decoy. The jog detector should also flag angle errors that are not caused by ECM, for example, those caused by idiopathic seeker behaviors such as a spontaneous angle search or a spontaneous partial survey scan or a spontaneous full survey scan. It should also flag target reacquisition when a pointing error suddenly becomes zero. That's when the seeker points its antenna back at the ship, or the target. Now, some people say that jog detection is a discredited idea because it has been tried before and every attempt has failed. Now, irrespective of previous attempts, with 100% certainty, it is possible to design a jog detector that correctly identifies seeker antenna jogs caused by ECM. There's no question that can be done. The question is whether it can be made to work under a sufficiently broad set of engagement conditions that the jog detector can meaningfully contribute to ship defense against missile attack, and also whether or not that contribution is big enough to warrant the cost of designing, developing, evaluating, and commissioning the jog detector. So we need to answer all those questions. But it's definitely possible. Part 2. Simple jog detector design. Now, perhaps the simplest jog detector is one based on measured seeker power rate. I'm not going to get into why that is, doesn't matter. Here's an example graph of measured seeker power level versus range for a sea skimmer missile. And here's the corresponding seeker power rate graph. And here is the jog indication logic signal. Let's zoom in here. Now, when the power rate is more negative than the threshold value, the jog indication logic signal is true, and it's false otherwise. Notice how the width of the jog logic signal changes as the indication threshold is made more positive. Use of the jog logic signal, whether it triggers an action on the leading or trailing edge or elsewhere, is a separate issue that it's not addressed here. Part 3, multipath. Now, of course, the main complication is multipath because it causes power fluctuations when there are no jogs at all. In this study, there are 2 propagation models of interest, and they affect multipath: a curved earth model and a sea swell model. And there are 4 other complications. The first complication is wind speed, which affects sea surface roughness. Surface roughness affects propagation depth, so it affects measured seeker power rate. The second complication is missile flight profile. This affects geometry, so it affects power rate, power level and power rate. The jog detector needs to work for sea skimming missiles and for high diving missiles. The third complication is missile altitude noise. As the missile flies, it sinks and lofts in a small amount, so it doesn't follow a mathematically perfect path. Because the wavelength is small at seeker frequencies, it's measured in centimeters, small changes in altitude can have a big effect on the seeker power level and rate. Here's multipath for a skimmer following a mathematically perfect flight path. Now, if you go to a familiar foreign test facility, this is the kind of graph that's produced by the facility's multipath model. It looks exactly like this, including the funny break that happens when the missile performs an altitude change. Now, here's what happens if we add altitude noise. The fourth complication is frequency. Pretty obviously, multipath is a function of frequency because it changes the wavelength. We want a jog detector that works at X band, Ku band, and probably Ka band also. So here's what happens if we add frequency agility. It produces power level noise. And this causes even more power rate noise since differentiation is a well-known noise enhancer. Part 4. Jog detector design. Now there are many possible elaborations on a simple jog detector, but this video addresses only the simple design based on measured seeker power rate. So here's the technical approach. Step 1. Do several tens of thousands of missile flyout simulations in which the missile attacks an unprotected ship. So we know there are no jogs, only multipath. The simulation runs must cover a sufficiently broad cross-section of engagement cases involving missile type, propagation model type, wind speed, and altitude noise and frequency. Step 2. Write a custom application to automatically perform several types of analysis on the subpopulations of these runs. A subpopulation means a combination of frequency, missile type, propagation model type, wind speed, and altitude noise. And it should be possible to perform analysis on combinations of subpopulations, for example, analysis of all sea skimmer cases or all sea swell cases irrespective of missile type, frequency, wind speed, or altitude noise, for example. It's especially crucial that the application automatically confirm that all the runs in a data directory for a given subpopulation actually belong to that subpopulation. It's very easy to make a mistake, so we need to make sure that there's no possibility of a configuration management error. The application should also allow the user to look at single simulation runs so the user can perform a forensic analysis for 2 reasons. Firstly, to understand the phenomenology of what's happening in a given engagement in a single run. And secondly, to confirm that all the bugs that are inevitably created during software development have been found and fixed. And you can see these things by looking at single runs, in many cases. Step 3. For each subpopulation of interest, calculate the statistical properties of the measured seeker power rate as a function of missile range from the ship. Now, statistical properties means the mean, specifically this. It means the mean seeker power rate as a function of range, the standard deviation of that mean, and the confidence interval of the standard deviation. The confidence interval means the area under the PDF curve between the standard deviation low and high limits. And here's an example. Graphs like this will provide some assistance in making an initial guess at the rate threshold for a jog detector, and also the range at which the jog detector will fail. And that's a really important point. The jog detector will not work at all ranges in all engagements. Whatever the jog detection threshold is set at, and no matter how complex, or probably no matter how complex the design, multipath will eventually cause false jog indications, for example, in the last kilometer. The objective is to design the jog detector that works down to a threshold range below which it doesn't much matter whether it works or not, because the engagement's over. If you haven't closed the deal in the last 2 or 3 kilometers, you're probably not going to. Step 4. For a range of jog detection thresholds informed by Step 3, calculate the probability of one or more false jog indications as a function of missile range for subpopulations of interest. For example, perhaps Step 3 indicated that a jog threshold of minus 25 dB per second will work down to a range of 3 kilometers for, let's say, a sea skimmer missile. We might calculate the probability of at least one false jog indication as a function of missile range, remember, for jog threshold power rates from, let's say, minus 15 dB per second to minus 40 dB per second. So we see minus 25 dB per second, so we're going to look at minus 15 to minus 40. Get a different graph, a graph for each one of those candidate values, like in 2 dB per second steps or something. As the jog detection threshold gets lower, we expect the probability of observing at least one jog, false jog, the indication that is, at a given range to go down, and which, by the way, it does. Step 5, and this is the hard part, relate the probability of false jog indication to ECM effectiveness. Now we want to do this because it lets us assign a performance score, a meaningful performance score, to each jog detector design. The catch is that the performance score is tied to the jammer design and operation. Now this is sensible since the jog detector is useless by itself. It's just a sensor. And we know that the best jog detector design for our purposes, because we want to protect a ship, is one which maximizes the ECM's ability to protect the ship. An evaluation of the quality of a jog detector must also include the jammer that uses it. It's worth adding one extra comment here. For this simple jog detector design based solely on measured seeker power rate, the probability of a false jog indication goes down as the power rate threshold is lowered. But we can't just lower it indefinitely because the detector will miss real jogs. The detector's power rate threshold needs to be low enough to reject false indications caused by multipath, but not so low that it will miss true jogs. The jog detector has an operating regime because the power rate caused by multipath is a function of range, whereas the power rate caused by ECM is not a function of range in the case of, for example, cross-pole jamming, although technically it is a function of range if the angled error is caused by, or the jog is caused by an off-board decoy. Now, treating issues like this is outside the scope of this video, but this little discussion gives an idea of where the thinking and the design needs to go. Anyway, this video does not cover step 5. Part 5. Some results.